Speaking of which, our next speaker is Tristan Ritchie. Tristan is a BEng in Computer Systems Engineering from the University of Bath, and he's a software engineer at an engineering consultancy called Cambridge Design Partnership. The topic of Tristan's presentation is RT thread for field-orientated motor control. So, Tristan, please take it away.
Thank you, Max. Can everyone hear me and see my screen?
Yes to both.
Excellent, excellent. Well, firstly, good afternoon, good morning, good evening to everyone. Thank you for tuning in to my talk today about real-time operating systems for power electronics, in which I'll be describing how high-performance motor control can be implemented using RT thread, and also how the RT thread kernel can be optimized more generally for power electronics applications. So to give a brief presentation about myself, I'm a software engineer at Cambridge Design Partnership, which is an engineering consultancy based in Cambridge in the UK that deals with many industries, but my focus has been on medical software, IoT devices, and power electronic software. I've recently completed my degree at the University of Bath, where my research over the past year has been focused on how real-time operating systems can be used in power electronics applications. The objective of the presentation today is to introduce some common requirements for power electronics software through the lens of motor control, and to show some of the challenges that are faced in industry with regards to power electronics software, and how the real-time operating system might be used to overcome some of these limitations and challenges. Generally speaking, power electronics software describes basically any software that is involved in electric motor drives, power conversion, such as renewable energy generation and distribution, but also things like energy storage and fast charging in battery management systems, and other applications like that. So from this, we can see that it touches quite a few industry sectors that are growing quite rapidly, most notably EVs, electric vehicles, and the renewable energy sector. But for this reason, it is quite important that we understand how this software is implemented at scale and how it can be verified before use in safety critical systems. One example of power electronics software that I'll be presenting today is field-oriented motor control, or FOC for short. It is a commonly used high-efficiency, high-performance multi-phase motor drive and control method that implements some high-bandwidth control systems that might be executed anywhere between a few kilohertz to perhaps hundreds of kilohertz. And FOC comes with some rather strict timing constraints, timing requirements in order to achieve good performance. And in fact, this is really the key area of my research this year. The key point here in this diagram that I've added is that any latency in the execution of the control loop, whether it be in the sampling of phase currents, as we'll see, all the way to the output of the PWM signal, any latency in that operation can severely deteriorate controller performance. And so this sort of high level pipeline is supposed to illustrate how any variability in sampling points can severely deteriorate performance. In order to go further into my implementation, I'll briefly describe the permanent magnet synchronous motor, which is the topic of this discussion. The PMSM for short is an AC motor which is composed of at least 3 electromagnetic phases that produce a magnetomotive force when current is applied. Those are shown here as phase A, phase B, and phase C. The rotor, on the other hand, is embedded with permanent magnets that produce a static magnetic field. And it is the interaction between the stator MMF and the rotor which produces torque. And in fact, the maximum torque per amp, the highest efficiency region of operation for these motors, is when the stator MMF is orthogonal to the magnetic flux of the rotor. But this is problematic, of course, because as the motor spins, we have to continually adjust the angle of this stator MMF vector that is shown in this diagram as Q, what we also call the Q-axis current, which represents torque. In order to produce this rotating vector, we need to apply sinusoidal voltages to each phase. And these are generated by varying the pulse width modulation duty cycle, which is input to a half-bridge inverter circuit in order to increase the voltage to our desired motor voltage. And this voltage is then time averaged over the inductance of the motor to produce sinusoidal current, which is shown here. In practice, we don't just want to produce a rotating vector. We actually want to be able to control the torque applied by the motor. And this corresponds to the magnitude of the stator MMF vector Q, and also the amplitude of these sinusoids represent the same thing. And so for this, we use closed loop feedback control, which requires the sampling of the individual phase currents. And we'll see that the timing of these phase current measurements is really quite critical to the stability of the control system. My implementation uses the STM32F429ZI, which is a Cortex M4 based MCU, which runs at a clock speed of 180 megahertz. The timing for the control system is provided entirely by the PWM timer. The reason why we don't use a more arbitrary delay function or something of that nature is because we really need to be sure that we are executing our control loop at a very regular intervals, and that there is no latency and delay in that execution. And so we'll use a PWM timer to generate an event which will trigger an ADC conversion directly in hardware. Again, the reason why we don't use a software conversion for the ADC is because we don't want to be relying on arbitrary code execution time for the timing of that ADC current measurement. When the phase current ADC conversion is complete, we will then proceed to the ADC interrupt handler, where we will execute our torque control at 20 kilohertz directly in the ISR, interrupt service routine. There are a few key things to note here in what I've described, which is rather advanced peripheral configuration. And that is that this sort of functionality is not currently supported by the RT-Thread BSP, nor is it really supported in general by any real-time operating system. And this is one of the main reasons why field-oriented control is typically implemented on bare metal, meaning that there is no real-time operating system. This use of bare metal software poses some rather important problems. On the development side, firstly, this is problematic because each implementation of field-oriented control must be specific to the hardware in the application, which requires the developer to reinvent the wheel, as it were, every time it is required. And this in turn inflates development timelines and costs, as these are rather complex systems. This includes not only the control system itself, but also the parallel functionality that is required to integrate the controller into the larger system. Things such as communication. In an EV, of course, the motor doesn't just spin by itself, it must communicate in a wider system. And in bare metal software, this often leads to the use of sort of rather arbitrary ad hoc communication protocols. Perhaps more importantly than this is the safety risk posed by bare metal implementation. The required interrupt-driven design requires quite a large amount of computation to take place directly within the interrupt service routine, and leaves other elements such as control loop synchronization or communication to the developer. And this can lead to rather unpredictable execution time and memory utilization. And so, I mean, overall, this makes it really quite difficult to actually validate and certify the software for use in potentially life-threatening situations, such as EV or medical instruments. And so we really have to think quite carefully about how to mitigate these problems. Now, one potential solution is to simply use a real-time operating system. In this case, if the BSP could be amended to support this sort of peripheral configuration, we would be able to rely on it for portability. We could also rely on the robustness and safety features that are guaranteed by the real-time operating system, such as memory safety and, or more generally, memory management. And execution in general can be moderated by the real-time scheduler for less latency-sensitive controller components, such as speed control, for instance, which will generally be executed at a much lower frequency than torque control, perhaps in the range of 1 kilohertz. However, this begs a couple of key questions that I hope to discuss in this presentation. The first of which is, well, firstly, how can RT-Thread be modified to support field-oriented control? And secondly, what are the performance penalties associated with using RT-Thread for motor control? The main drawback of the RT-Thread BSP as it stands is the limited configuration options, specifically with regards to the ADC and PWM drivers. To get around this limitation, I've implemented additional driver codes that allows for these more advanced configurations. For the ADC driver, this required adding code to handle and enable ADC interrupts, but also to enable what are called injected channel conversions, which are effectively high priority conversions that preempt the ADC. And lastly, I've added support for hardware triggered conversions. As mentioned, these are used to guarantee the moments of sampling on the ADCs. On the PWM driver sides, I've added support for center-aligned PWMs, as these are vastly preferable for motor control for a number of reasons. I've also added support for timer trigger signals to trigger the ADC conversions. And I've also made some optimizations to the PWM duty cycle update system in order to cut down on some of the overhead involved in that operation. However, we do still need to consider the performance implications of using the real-time operating system to determine whether it is actually suitable for high-performance control. And we'll take a look at some of that analysis now. Now, I will just start with a small disclaimer that most of this analysis relies on code execution profiling, which is, of course, dependent on the hardware used the clock speeds, the architecture, things like that. But it should at least give us an indication as to how the operating system should be used in most applications, at least. This first test shown here demonstrates the excellent interrupt servicing capabilities of RT-Thread. And in fact, along the bottom, these two images show profiling measurements taken from a bare metal implementation shown on the left, and the RT-Thread implementation shown on the right, where each edge of channel 2, shown in blue, represents one ADC conversion complete interrupt, and the 20 kilohertz PWM signal is shown on the bottom in yellow. We can see that there's virtually no difference between these two images, which shows that RT-Thread interrupt servicing is absolutely suitable for field-oriented control. However, this isn't quite the whole story. Using an RTOS generally means that we'll be working in a multi-threaded environment. And of course, most of the kernel code, such as scheduling or manipulating concurrency primitives, will execute with interrupts disabled. And this will certainly impact the latency that we've measured here by introducing some delay of some magnitude. And so it'd be quite interesting to actually measure that. Perhaps the most common thread synchronization mechanism is the semaphore. In this example, the semaphore is released at the point of interrupt, again on this rising edge, and then a context switch is immediately generated after some overhead. And we've here measured the point of servicing, which is the point where the semaphore is actually taken by a worker thread. And we can measure this latency to be in the range of about 8 to 10 microseconds, which in this application represents about 15 to 20% of a single PWM duty cycle. Given that we only have 50 microseconds to do all of our processing and communication and closed loop control, this is really quite limiting. In fact, we spent a substantial portion of our compute time simply mucking around in the RT-Thread kernel, manipulating the semaphore and figuring out which thread we want to wake and context switch to. What this really shows us is that in general, semaphores probably should not be used in power electronic software, as again, interrupts are disabled throughout this operation. And if we happen to be manipulating some semaphore when our ADC interrupt comes in at this point, we will not be servicing that until a later point. And that is not really acceptable in field-oriented control. And so, well, how do we get around this? Well, I've tried to get around this by implementing a new feature, which I've called direct context switching, which is effectively a low overhead method of context switching, where instead of manipulating a semaphore kernel object and running the entire scheduling function, I'm simply passing the destination thread as an argument. In this case, the developer is explicitly telling the scheduler where they want to go. And this cuts through a lot of the overhead associated with manipulating concurrency primitives, like the semaphore kernel object, as well as a lot of the scheduler overhead that is required to figure out which thread we want to run. Using this mechanism, we can trigger a context switch much faster and reduce the time spent with interrupts disabled. Note here the difference in time base for this measurement. We've reduced the servicing latency by about 50–55%. And in practical terms, this allows us to accomplish quite a lot. And I'd like to go into a little bit more detail here on the concept of interrupt servicing bottom half. What is an ISR bottom half? Well, it is effectively a mechanism to split the interrupt servicing routine into two separate components. The ISR top half will run immediately in the interrupt handler, and this should include all of the very latency sensitive operations, such as torque control. However, using this fast context switch mechanism, we are actually able to delegate quite a lot of the other processes that are synchronized to the ADC interrupt, such as maybe lower bandwidth control systems, speed or position control, high frequency communication, plant condition monitoring, things like this. And so we've effectively managed to delegate a lot of the processing to a thread mode task. And this is useful because, of course, we'll have access in the thread mode to all of the memory safety, stack overflow checking capabilities of the real-time operating system. Implementing this in RT threads is perhaps a little counterintuitive, as RT thread is supposed to be a hard real-time operating system. And by bypassing the scheduler in this way, we've effectively created a soft real-time kernel, as this bottom half ISR thread cannot be preempted by another regular thread. So this is what we'll call soft real-time operating. That said, we still benefit from memory management and fault handling. So it's perhaps a trade-off that we're willing to live with in power electronic software, at least. When it comes to inter-process communication, there are quite a few options available to us in RT thread. Since manipulating concurrency primitives, like synchronization primitives, requires interrupts to be disabled, it is important to try to understand the performance implications of each of these methods. Perhaps the most traditional method of moderating access to a shared memory resource is to use a mutex. Now, this is similar to a semaphore in that it has quite a sizable overhead. It is quite an expensive primitive to manipulate. And it is important to note also that the mutex cannot be used from an interrupt handler, as it introduces concepts such as thread ownership and things like this. It really should not be used in the interrupt. But the key point here in the mutex, like the semaphore, is that it simply has too big a performance impact to really be justifiable in a power electronics software application. Instead, we should aim to use critical regions, which simply disable the scheduler. This is a bit of a workaround, but it still helps us manage shared memory between two threads, as while one thread is accessing a shared memory resource, the scheduler will not preempt that thread. It also helps avoid certain nasty race conditions, deadlock, priority inversions, things like this, that the developer generally wants to avoid, or definitely wants to avoid. It's also quite a bit more lightweight than the mutex and requires only a few lines of code to execute. The disadvantage of the critical region is that it cannot be used, like the mutex, it cannot be used to moderate shared access to a shared memory resource between a handler, an interrupt handler, and a thread. For this, we should simply manually disable interrupts. This has the effect of disabling the scheduler, but also disabling other interrupts, so it cannot be preemptive. And this will, of course, avoid any spooky behavior when it comes to a shared memory resource. Now, Of course, disabling interrupts will have a negative impact on interrupt servicing latency, but as long as we keep those data transfers, those inter-process communications fairly short, that impact will be equally short. If we do want to transfer larger amounts of data, we should probably use the mailbox, which has a significantly lower overhead to the mutex, as it is structured more like a message passing interface. But again, it is still not great and requires about 6 to 8 microseconds of latency with interrupts disabled. So in practice, we should really try and avoid big data transfers between processes, but when necessary, we can use critical regions or areas with disabled interrupts. To summarize, the key points that I want to communicate in this presentation are that the real-time operating systems could serve to greatly benefit power electronics software, specifically with regards to software portability and software safety. I hope I've shown how RT-Thread in particular can be optimized for power electronics to provide low latency interrupt servicing, context switching, and lightweight inter-process communication. And of course, in particular, how the soft real-time kernel is perhaps better suited to power electronics than a hard real-time kernel. To finish up, I'd just like to show some waveforms that I've taken from my implementation to demonstrate functionality. Unfortunately, I'm not able to give a full demo at this point as I'm not in the labs, but at least these waveforms will show some of what you would expect to see. This top waveform shown here is the output of the PWM, or is the time averaged PWM voltage from the PWM outputs. And you might think that this doesn't look sinusoidal in shape at all, and you'd be right, because we've actually performed some additional modulation here to achieve greater DC bus voltage utilization. But we can simply add the, I should probably say that to generate these systems, we've effectively removed the common mode between the sinusoids. And by adding that common mode back in, which is this green triangular wave, we can see some very beautiful clean sinusoids that will produce nice smooth rotation in the permanent magnet synchronous motor. That concludes my presentation today. I think I've left a couple of minutes for questions. If anybody has any, feel free to drop them in the chat or unmute yourselves.